Okay guys, so here's the lesson for sections 4.5 of pre-calculus. Okay, so let's take a look at that. It's all the word problem. So exponential and logarithm with word problems. Word problem, not word problem. Okay, so let me fix that one here. Okay, all the word problems. Application problem. Okay, so the population of a certain city was 115,000 in 2000, the year of 2000, and now it grows at a rate of 4% per year. And find a function that models the population up to t years. So anytime that we deal with a problem like this, so one thing that I need to recognize is about the formula that we need to apply. So one thing we do know is that it's the y of t, exponential growth model. So y of t, so that equals y of 0. So times e to the power of kt. So now let me explain what this means. So y of t is the final population after like certain time. And then y of 0, that's the initial population. Okay, so this one is the initial population. And then k is just a constant. And one thing that we notice for e is the exponential constant. So e is about 2.7 something. And then t, that's just the time. So basically this one, we just want to find out the model. Okay, so one thing we notice, so the initial population is 115,000. So that means y of t equals 115,000 times e to the power of kt. So that grows at the rate of 4% per year. Okay, so 4% per year. So this one basically gives you the constant rate, 0.04 times t. And then find the projected population in the year of 2005. Okay, so in the year of 2005 to 2000, that's about 5 years. So y of 5. So 115,000 times e to the power of 0.04 times 5. So this one you can use a calculator to find out exactly what that is. So try to do that on the calculator, on the Android, or on your iPhone, or any scientific calculator or graphing calculator. You'll get 115,000 times e to the power of 0.04 times 5. So the population would be about 140,000. Whoops. Did not read through that. Undo. Okay, let's undo all this. So the final population would be about 140,461. Okay. And now the next one, it's a half-life problem. So half-life of a cesium-137, that's just like a compound name, chemical compound name, is 30 years. Okay, so suppose we have 10 gram sample, and find a function that models the mass remaining up to t years, and how much of the sample remain after 40 years. So first thing we do know is that in order to get to the half-life, it takes 30 years. So that means 1/2 of the initial amount. So that equals the initial amount times e to the power of kt. So k, we don't know what that is, but we do know the time. In order to take to the half-life, it's what? It takes 30 years. So 30 times k. So first thing that you want to find out is the value of k. So y of 0, you can cancel them out. So we do have 1/2 equals e to the power of 30k. And then you want to solve for k. So take the natural log. So natural log of 1/2. And then natural log of e to the power of 30k. So we do have natural log of 1/2 equals 30k. And then by using the properties of logarithm, so natural log of 1, that's 0. And then natural log of 2, so then that would be considered negative. Natural log of 2 equals 30k. Again, we do know that natural log of 1, it's 0. We use the quotient to the difference property. So that's why we end up with this. So that means k equals negative natural log of 2 divided by 30. So once you rewrite the equations, so eventually the equation is going to be considered, well, the first part of it, you want to find the functions. So the function would be considered y of t. So that equals the initial amounts, so 10 grams. The initial amounts for the compound. So 10 times e to the power of negative natural log of 2 over 30 times t. So that would be the general model and for the functions. So for part A. And now what about for part B? So you want to find out the amounts after 40 years. So just plug in the time, 40 years. So 10 e to the power of negative natural log of 2 over 30 times 40. So we try to do that on the calculator. Let's see what we can come up with this. So you try to do that on the calculator. You get 10 second base e to the power of negative natural log of 2 divided by 30. And then times 40. Because that takes 40 years. So I got about 3.96. So this one eventually, it's about 3.96 grams. Okay, for the sample remain. Again, it's a exponential decay model. Now, what about for C? So how long would that only take 3 grams of the sample remain? So 3 grams of sample, so that means, well, let's do it right here. So for C, so you want to set that 3 equals 10 e to the power of negative natural log of 2 over 30. So this time you want to find out the time, the number of year it takes to get down to 3 grams of the remaining sample. So let me set up the new slide right here. So let me copy down the equation first. So what we got here, it's a 3 equals 10 e to the power of negative natural log of 2 over 30 times t. Okay, so let me transfer that to the new slide. Oops. So this one I want to go to the next slide. New flip chart. Okay, so now, here we go. So what we got for the equation, once again, we do have 3 grams for the final remaining sample. And then, so the initial amount is 10 grams times e to the power of negative natural log of 2 over 30. And then times the time, t. So in order to isolate the variable, we divided by 10 on both sides. So 3 over 10. So that equals e to the power of negative natural log of 2 over 30 t. And then take the natural log both sides. So we do have natural log of 3 over 10. And natural log of e, that just 1. So just bring down the power. We got negative natural log of 2 over 30 times t. And then in order to isolate the variable, we divided by negative natural log of 2 over 30. Okay, so let's find out what the time is for this one. So to do that on the calculator, well, you have to use the calculator for this. It's a non-calculated problem. It's a calculated problem. If you try to do it without the calculator, it's very difficult. So natural log of 3 over 10 divided by negative natural log of 2 over 30. So we need to put in some parentheses for the quantity. Okay. And let's see what I end up for this one here. So the time it takes. So it's going to take 52 years. Okay. Well, it makes sense. If you just go back to the previous problem. So the one, in order to get to 3.96 grams, so it takes 40 years. In order to get a little bit more, well, even less. So that means it's going to be taking much more time. So it's going to take about 52 years. Okay. So now let's see what else that we have for the next example. Again, this one is all about the exponential growth and the decay model. So here's another classic one. It's called the Newton's law of cooling. So for the Newton's law of cooling, we do have a formula such as this. So for the Newton's law of cooling, we do have a temperature of the object. It's called capital T of the time, little t. So that equals the initial temperature of the object minus the surrounding temperature. So surrounding temperature is like the temperature of the room, and then times e to the power of kt, well, negative kt, and then plus the surrounding temperature. So initial temperature of the object, so here's T0, or we can say that it's T0, initial temperature. And then Ts, that's called the surrounding temperature. And then K, again, that's just a constant. And then T is just the time. And then again, Ts, the surrounding temperature. Okay, and then capital T of T is the final temperature after like certain time. The final temperature of the object. Okay, so now let's just read through the word problem. A scale full of water is brought to boil in a room temperature of 20 degrees Celsius. So 20 degrees Celsius. So let's just annotate it. It's the surrounding temperature, Ts. It's a degrees Celsius, not Fahrenheit. So after 15 minutes, so the time, and the temperature of the water has decreased from 100 degrees Celsius to 75 degrees Celsius. So find the temperature after 25 minutes. Okay, so started with the initial temperature, 100 degrees Celsius. So now it drops down to 75 degrees Celsius. So 100 degrees Celsius, then that'll be the final temperature. You can say that T of T. And then 75 degree, that's called the initial temperature. So it looks like K is missing here. So we need to solve for K first before you do anything else. So first thing that you want to do, you want to solve for K. So the final temperature of the water is 75 degrees Celsius. So that equals the surrounding, well, the initial temperature, which is 100 degree, minus the surrounding temperature. So let's just put in those numbers. Times e to the power of negative kt. Again, k, we don't know what that is. But the time it takes 15 minutes, so negative 15t, negative 15k. And then plus the surrounding temperature. Surrounding temperature, what we got here, it's 20 degrees Celsius. So first thing that you want to find out is the difference of that 120. So we do have 80. So 75 equals 80, e to the power of negative 15k plus 20. And also, in order to get rid of the 20, you subtract 20. So 75 minus 20, you get 55. So that equals 80, e to the power of negative 15k. Now, you want to solve for k. So divided by 80, both sides. So we do have 55 over 80. So that equals e to the power of negative 15k. So 55 over 80, it's reducible. So it's divided by 5, top and the bottom. So you do have 11 over 16. Okay, so 16 times 5, which is what? 80. So that equals e to the power of negative 15k. And then solve for k. So you take the natural log both sides. Again, natural log of e, that just 1. So we left with natural log of 11 over 16. So that equals negative 15k. And then solve for k. So it's natural log of 11 over 16 divided by negative 15. So that just gave you the value of k. Okay, so now let me just write down the information. And then I'm going to transfer this one to the next slides once again. So for the value of k, we do have natural log of 11. Natural log of the quantity of 11 over 16. And then divided by negative 15. And then the function we have, it's t of t. So that equals 100 minus 20, which is 80. E to the power of kt. And then plus 20. So just want to simplify it. So I'll transfer that to the next slide. Okay, so once again, So the value of k that we find out, so that it's a natural log, a ln of 11 over 16 over negative 15. And then for the Newton's law of cooling, the general equation is the final temperature of the object. So that equals 80, because that's 100 degree minus 20. So 100 degrees Celsius, that's like a boiling point of the water, minus 20 degrees Celsius. 20 degree, that's the surrounding temperature, so you get 80. And then e to the power of kt. So we just want to put it this way first, plus 20. Okay, so now let's see what the final question is. So the final question for this one, okay, I need to go back to that slide, 4.5. Okay, so the final question that you want to find out the temperature after 25 minutes. So find the temperature after 25 minutes. So we got 80. So e to the power of k, so k is negative. Again, this one's negative kt. So negative, so that turns out to be positive. Natural log of 11 over 16. And then divided by 15 times the time. So 25 minutes, so 25 times 25. And then plus 20. Okay, so once again, just want to go back to make sure that we're getting everything correct right here. 25 minutes, that's right, okay. So now, let's just put it into the calculator and see what happened. So we got 80 times e to the power of natural log of... So got to be careful with this. You have to use the parentheses. Natural log of 11 over 16. Open parentheses and then close parentheses. Divided by 15. And then times 25. Close parentheses. And then plus 20. So eventually the final temperature is going to be 62.84 degrees Celsius. Well, which makes sense because after a certain while the temperature is going to cool off. The water is going to cool off. So the temperature is going to drop down to 62.84 degrees Celsius. Okay. So now let's see what else that we have for the last example. So this one shows the pH scale for those of you taking chemistry. So I'm sure you guys know what that is. So it's the acid versus the base. So pH is negative log of hydrogen plus. Okay. So calculate the following pH scale for the substance. So tomato juice, so the pH scale, H plus is 3.2 times 10 to the power of negative 4 moles. Okay, so what we need to do here, we just want to take that negative log of 3.2 times 10 to the power of negative 4. And for those you might be wondering what this is, well, this one is just a scientific notation. So we can always expand it. So equal sign. Expand it. So we do have negative log of 3.2 plus, well, this one is a power to coefficient and also is a product because that's a multiplication. So minus 4 times log base 10. Okay. So I need a little bit more space here. So let me just get some space from the other part of the problem. Okay, erase all that. So now, for those you might be wondering, can I just leave it like this after expand it out with the properties of logarithm? Well, another thing that you need to do, you need to simplify it a little bit more. So this one, so that equals negative log base 3.2. So one thing that we noticed, log base 10 of 10, if the base is not shown, is always 10. So this one is just 1. So what's left here, it's just negative 4. But don't forget, it's negative, negative. So that turns out to be positive 4. And that'll be the final form for this pH scale. And then for the seawater, so basically we want to do the same thing. So again, so it's negative log, we just follow through the pH scale formula. negative log of h plus. So the given h plus value here, it's 5.0 times 10 to the power of negative 9. Again, that one is just a scientific notation. So once again, expand it, product to sum, power to coefficient. But got to be careful the way that you change the sign for the number. So eventually, you'll end up with negative log 5.0 or negative log 5. And then bring down the power, so negative, negative, so that turns out to be plus 9. Again, log base 10 of 10 is going to be considered 1. Okay? So I hope you liked the video, the lesson that I make today. So please, either you rewind it or you fast forward to catch up with things that you need more attention with. And let me know any questions. And also please refer to the people that are subscribing to the channel so we can get more extra credit participation point. Okay? So see you guys next time.